In this video, we're going to go through deviation from ideal gas law, and we'll be able to answer the question, why do real gases deviate from the predictions of the ideal gas law under certain conditions? All right, so ideal gas law, which is PV equals nRT, assumes two important things. Number one, no particle volume. Number two, we don't have any attractions between those particles. However, real gases deviate from ideal gas law at high pressure and low temperature. And we're going to dive into why that happens. So, ideal gas law assumes molecules don't have their own volumes. We assume that most of the container is empty space. And that's true. However, the volume of gas particles become negligible when we compress those particles into a small volume. So again, under ideal conditions, most of the container is empty space. The particles are negligible. They're really far apart. But again, at high pressures, molecules are compressed into a much smaller volume. And then the ratio of empty space to volume of particles becomes significant. So here's what I mean. Under normal conditions, or under ideal conditions, I should say, the volume of those particles is negligible because the particles are really far apart. There's a lot of distance between those particles. When we compress that volume, the particles are now much closer together, and now you have intermolecular forces that start to become an issue because the particles are a lot closer. Over further distances, IMFs don't play that big of a role, but when we compress those particles into a smaller space, now they're close enough where IMFs start to matter. So we have an adjustment that we can make. So if we have our new ideal volume, we're going to take the volume that we measured and we're going to subtract off the number of moles of a gas, and we will have a constant for the type of gas. So depending on what the gas is, we'll have a different constant. So we can now substitute in this, so V measured minus NB, into our ideal gas law equation for V. So this is a correction that we can make to ideal gas law. So as I mentioned, when we move everything into a smaller space, we have IMFs that start to become an issue because the particles are a lot closer. So as volume decreases, pressure increases. They're inversely proportional. Now, gas particles, when they're close together, the actual pressure that they exert on the container might be less than what the ideal gas equation is going to predict. So remember, in a sealed container like a balloon, you have all of these gas particles. They're bouncing around. Anytime they hit the wall of the container, that's basically the pressure that you're feeling on the container. So that force, that pressure is what you're feeling. Now, when we are compressing everything, when we have high pressure, the particles are a lot closer together. When that happens, particles around the other particles start to exert forces of attraction, and those particles are going to start basically slowing down the particles around them. So because the particles are not moving as fast as they normally would, you're going to end up with less pressure than you would assume. So in a low pressure system, notice we have this particle. There's nothing around it, and it's able to hit the wall of the container unobstructed. There isn't anything getting in its way. It can just ricochet off the side of the container. However, in a high pressure system where the particles are a lot closer, notice now we have all of these particles that are around our particle that it's attempting to bounce off the side of the container. And now those other particles, the IMFs that are occurring, are going to slow down the green particle. So now the force of attraction is going to be the forces of attraction are going to reduce the impact velocity. So it's going to hit with less kinetic energy than it would because the other particles around it are slowing it down. So just like we had a different equation that we could use that would account for this discrepancy for volume, we also have one for pressure. So we'll take the pressure that's being measured and we're going to add in this adjustment. So it takes into account the number of moles of a gas. Again, there will be a gas constant. And then we'll also take into account the volume of the system. So we'll have this substitution. So if we take the two substitutions that we have that account for these variations, and we substitute those into the ideal gas law equation, so instead of it being PV equals nRT, we're now substituting in these corrections for pressure and volume, and we end up with van der Waals equation. Super complicated. You're probably not going to see it on an AP exam, but this is van der Waals equation. So van der Waals equation takes into account non-ideal behavior. All right, the other deviation that you can have occurs at low temperatures. So at high temperatures, particles are moving very fast. They're bouncing around, nothing's going to get in their way. However, at lower temperatures, gas particles move slower and are closer together. When they're moving slower, the attraction between molecules exists under these conditions. So think about if you're running by somebody in a football game and you're running by them really fast, it's really hard for them to interfere with you. But if you had like a lineman who are much bigger and slower in a game, they're not moving as fast, and it's a lot easier for other players to tackle them. Okay, so think about it in that sense. So high temperature, you're moving very fast. It's hard to catch you. It's hard to interfere with you. At low temperatures, you're moving slower, and it's a lot easier in a football game to tackle one of those players. Okay, the last phenomena we're going to talk about is condensation. So intermolecular forces increase as the distance between the particles decrease. So if I have two particles and they're further apart, IMFs are pretty weak, but as I move those particles closer, as the distance between the particles decreases, now the intermolecular forces are going to increase. There'll be a stronger force of attraction. This leads to condensation. So condensation is where you go from a gas to a liquid at low temperatures or high pressures. This applies to all gases, even those with weak intermolecular forces. Condensation can occur rapidly when the temperature of a system drops. So in this case, the kinetic energy of the particles is reduced, so they're moving slower, and then they're going to move closer together, like we have up here. This is going to cause the particles to kind of stick together when they collide. Condensation can also occur at high pressures, where particles are closer together, and because they're closer together, they're going to experience a higher rate of collisions. So we've got box A and we have box B. So box A, you've got two particles. They're not really close together. Box B, let's say we compress a bunch of particles and now we've got them in the same amount of space. So obviously there's more particles, there's going to be more collisions. So when you have a gaseous system and it's approaching the condensation point where we go from a gas to a liquid, the forces of attraction between the particles are at a maximum. This is the largest possible decrease in measured pressure, and you'll see a large deviation from ideal behavior when this happens. All right, so let's look at some examples. So this first one says, which of the following gases would deviate least from ideal behavior at 1 atmosphere and 25 degrees Celsius? So we have three molecules. So we have NH3. So NH3 looks like this. We have CO2. CO2 looks like this. We have oxygens that are double bonded to our carbon. And then we have helium. Helium gas is basically just helium floating around. So in our NH3, we have London dispersion, we have dipole-dipole, And we also have hydrogen bonding that's occurring here. So we have in a container that was just NH3, we have hydrogen bonding, which is a relatively strong intermolecular force. For our CO2, CO2 has London dispersion, and that would essentially be it. So we have LDFs going on. And then helium, we're just going to have LDF because it is nonpolar. Okay, so it says deviate least. So where things are going to deviate least, we've got a constant pressure and we have a constant temperature here. But let's think about this in terms of intermolecular forces. So stronger intermolecular forces are going to have a larger impact on how gases behave. So NH3, because we have hydrogen bonding, and hydrogen bonding is a strong IMF, that is going to deviate from ideal gas law. So we're going to see unusual behavior, or not ideal behavior, because the intermolecular forces are going to affect the other gas particles, similar to what we saw here. Okay, so if these other particles, these purple particles, are a lot bigger and stronger, they are going to have stronger attractions, and again, you'll have ricochets that are going to be less than expected here. So you'll have lower pressures, and you'll see deviations from behaviors. Okay, so we're left with CO2 and LDF. Or sorry, CO2 and helium. So both of those are LDF. However, helium is a much smaller molecule. We just have helium floating around. It also is a noble gas and it's non-reactive. So between these two, helium is a smaller molecule. It's going to have weaker intermolecular forces and therefore would deviate the least. So those particles are going to be moving very fast and there's not going to be a lot of attraction between the particles. All right, let's look at this last question. It says, under which set of conditions would a real gas behave most ideally? So ideal gas law happens at low pressure. So the particles are spread out. And high temperature. So the particles are moving very fast. And because they're moving so fast, all the other particles around them, they just don't care. They're just moving so fast that doesn't really matter. So low temperature, high pressure. So our lowest temperature and our highest pressure in this case would be choice B, 1 atmosphere and 300 Kelvin. And that in a nutshell are the deviations from ideal gas law.